Oh man, you see a lot of us in this one.
Oh,
Yeah, I
no.
guess probably kind of zoom in so people.
There we go.
All right. So we finished up last time talking about writing up our contrasts and things, okay? If you're feeling apprehensive about contrasts, understand, but just recognize that it's just a t-test, right? At the end of the day, we're just combining certain groups with certain groups, and it's a really nice and flexible way to go through and start to consolidate some follow-up tests for your ANOVA types of designs, okay? Then we've also got our post hoc comparisons, all right? As we had mentioned, as we talked about last time, having some set of small planned comparisons, this is always going to be your best bet. This is showing that you've thought ahead, that you have a clear understanding of your research question, your design, and you're saying, hey, there are lots of different things I can compare, but these are the things that are going to be most central to addressing the question that I have, okay? If I go through and look at all possible comparisons, most of the time, only a fraction of those comparisons are going to be interesting. Like, it's a free country, I can do whatever I want, compare whatever I want to. It's just that those comparisons probably aren't going to be terribly interesting from a theoretical or conceptual standpoint. And if I go through and appropriately account for all of the potential alpha inflation and enact controls for the comparison of all those tests, what that ends up is it's going to go through and it's going to impact my power. Okay, we already know that our tests tend to be underpowered. And what I'm essentially doing is adding more stringent controls to run comparisons that I don't really care about or am not really interested in anyway. So thinking about and putting together a game plan before you go through and even run your analyses is going to be your best bet so you can don't get trapped in post hoc hell, okay? But there are some situations where in exploratory situations, maybe just looking at, hey, what's different than what else can be or informative, okay? This should probably be the minority of the cases, but it's certainly something that we can go through and do and take a look at, okay? Thing with post hoc tests, we've got a lot of different ways we can go about through and do this. Pros and cons of different approaches. If we go through and look at history of methodology and behavioral sciences, lots of different procedures, approaches that people have taken to try and go through and adjust for, correct for the evaluation of multiple comparisons after running an omnibus test like our ANOVA stuff. Okay, so our most basic in terms of post hoc approaches is something our procedure we call Fisher's least significant difference, LSD, right? Fisher's drugs, Fisher's LSD. The rule with Fisher's LSD, all we need to have is just a omnibus effect, right? If we get an omnibus effect that warrants interpretation, right? Meaning traditional standards for statistical significance, Fisher's least significant difference says that, hey, once we got that, that's the green light to go forward and just go nuts, okay? With Fisher's, what we're doing, again, it's the same variation on a t-test procedure that we had talked about before, okay? It's just the comparison of your two groups divided by the square root of the mean squared error for group one, mean squared error for group two, right? So it's just a t-test formula. We're just substituting mean squared error from my overall ANOVA table in for my pooled variance, right? And then what I do is I compare my test statistic here against a critical D with degrees of freedom error from the overall ANOVA table. Okay, so this is just the same thing that we had talked about with the a priori contrasts. This is just with Fisher's least significant difference. What we're doing is we're doing this for all possible pairwise comparisons within my set of means. Okay, and again, what we're doing is we're benefiting here with Fisher's from using the error variance term from the overall model, right? My mean squared error term from my overall ANOVA table is just the pooled variance across all my groups, okay? So we're benefiting from more people in the sample, which should give us a more precise, in theory, give us a more precise estimate of the variability. And then we're comparing that against a critical value with degrees of freedom error from your overall ANOVA table, which is going to be much larger than it would be for what the degrees of freedom would be for an independent sample t-test. Okay, so you're definitely capitalizing on power here. And what we know is that Fisher's is the most powerful post hoc test of the post hoc testing procedures we have. Okay, but criticism is that Fisher's doesn't actually manage any family-wise error. Okay, Fisher's just says, hey, if I get that omnibus effect in my overall ANOVA, jailbreak, right? I can just go and sort of test everything I can using a relatively powerful test because we're using a lower critical value because we're pulling degrees of freedom from the overall table. And so you can go through and do this. The problem is it's a post hoc testing procedure. It just doesn't actually add any type of actual control for inflation of type 1 error here. Okay, so if you've got a simple design with maybe 3 levels, right, to your factor, you got 3 different groups, you might be able to get away with running that with Fisher's, but the problem here is that there's not any actual sort of correction for this. You just get that omnibus effect and then you just kind of take it off from there. Questions about this? Yeah.
What does FWE stands for?
What's that?
Family-wise error.
Family-wise error. Yeah.
That's the thing that we were talking about with doing multiple tests, like the errors compounding,
Yeah,
like
yeah.
3 of them.
Yeah.
So then if you're doing this, are you reporting this after, like, oh, this is a weakness of LSD?
You could,
Okay.
or you would maybe want to justify that, you know, you want to say, hey, we're really exploratory, we're worried, we don't want to, we're fine if like, we're just scoping this out, completely
Okay.
exploratory. If we find something, we're not making a big deal about it right
Okay.
now, we're just trying to get a signal out for sort of moving forward, so we're just gonna go ahead and kind of use this, right? Now, you might get a reviewer that says, well, you used Fisher's doesn't actually control for anything, so you need to go back through and use a different one, which then you would need to do that, right? So probably hard if you're going into a completely exploratory post-hoc procedure to justify Fisher's probably, but it is an approach that people have used.
Would you not recommend? Like,
Probably not, right? If we're trying to think about running, particularly if you're running a lot of different comparisons. Yeah, this isn't, you're actually probably making things worse because you actually have more power here. So it's not only not controlling for things, you're actually capitalizing on the power of the overall design. So some problems with this. All right, so what we have instead is our Tukey and the studentized range statistic, okay? Who's excited about Tukey?
I've seen his name.
Everybody loves Tukey. Tukey's like the favorite, particularly around Thanksgiving, sounds like turkey, right? We like this, right? So it gets in your head, okay? Tukey and a number of different post hoc procedures we'll go through and talk about are based on what's known as the studentized range statistic, Q statistic, okay? And what our Q statistic is doing is it's going through, and it's a table. Do you have that Q table? Okay. What we're doing is we're just, for anything that's using our studentized range statistic, what we're doing is we're just pulling up a different critical value that's more stringent than what we would see with a normal t-test, okay? With all of these post hoc tests, they're just versions of t-tests, okay? Which is why I sort of really want you to understand t-tests because it's the basic building block of all this stuff we're doing. Tukey, same thing, it's just a t-test. We're just using a little bit different, we're calculating a little bit differently and using a different critical value here, okay? So for Tukey, our test statistic here is gonna be Q sub R, where R is given as the total number of means in your set, okay, or in your set of comparisons. So to calculate our Tukey statistic, pretty easy. Tukey is just saying we're taking the mean of the largest comparison or the largest group and the mean of the smallest group. We're doing a comparison there. If we're comparing those two, the largest and the smallest, and then we're just taking that over the square root of the mean squared error from our ANOVA table over our cell size. Okay, Now, this is assuming that we have equal, a perfectly balanced design. So N, make sure you note this, N isn't the total number of people in the sample, it's the total number of people in the cell. The assumption is that we have equal people in each cell. Okay,
And if we don't, we're not using two key.
we'll use a variation on 2, which we talked about. Okay, this is old school classic stuff, all right? But what's nice and what makes this kind of useful, and now we can start to play around with things a little bit, is our studentized range statistic, our Q statistic has a direct relationship with our T statistic, okay? And we can work back and forth between these two to make this a little bit more flexible approach. So our T squared statistic, at least as we calculate it based on our Fisher's LSD, remember, is the difference in means over 2 times the mean squared error over the sample, the cell size, right? So because of this, we can go through and see kind of the relation between these two. My T statistic is equal to just, or my test statistic for T is just Q over the square root of 2. Q is equal to T statistic times the square root of 2. So we can move back and forth between a Q statistic and a T statistic very easily. And we can start to use this in ways that make this a little bit more of a flexible approach, okay? Now note that this is a T statistic using the mean squared error from our overall ANOVA table to go through and calculate it, but we can start to play around with this a little bit, okay? So again, the thing here is what we're doing if we're using our Q statistic or any type of 2Q informed procedure. Again, we're using our studentized range statistic. And what we're doing here is looking at finding critical values based on degrees of freedom error here, like we would with the t-test, and R, which is going to be the number of, we call this, you'll see this sometimes referred to as the number of steps that you're making in this set of comparisons. So basically, we're just using a different table to get our critical value, okay? So what we would have here, let's say that I have a test with 20 degrees of freedom, and this is 20 degrees of freedom that I pulled from my overall ANOVA table. What I would do is I would say, okay, 20 degrees of freedom for my overall ANOVA table, and then I have a comparison of, let's say, 4 means, okay? And so I have 4 means, and I'm going to say if I'm comparing the smallest mean to the largest mean in that group, I would go to R, the number of steps or the number of order of means, go down through, take a look, 24, I get a critical value of 3.96, okay? And so then I would just go ahead and sort of run sort of my normal hypotheses test. It was just, I would compare that with my Q statistic and then a critical value of 3.96. Kind of following this procedure?
Following this, could I ask a quick question on the previous page real quick?
Yeah.
So we have QR up at the top and then you've got T and Q down at the bottom. Are those like functionally the same? Or
Yeah, they're the same. And we'll talk about why formally we have that sub R. It depends on what specific version of Tukey that we're using. Okay. So with Tukey, kind of what's going on, it's important to understand kind of the philosophy, like what's happening, sort of the idea behind this. Our Q statistic assumes that what happens, right, when we go through and we run, let's say we run our ANOVA, right? And you run your ANOVA and then you go through and kind of looking back, okay, I got an omnibus effect that says that at least one of these means is different than somewhere else, but I need to go through and kind of figure out where that is, right? So maybe you look at your descriptive statistics, you look at your means, you're like, oh, I wonder if these two groups are different. What's probably the characteristic of the two groups that you've gone through and looked at?
What do you mean? Besides they're different?
Yeah. What's going to probably stand out to you as being different about those two things? Are you likely to pick out the two means that look closest to one
Oh,
another?
the two that are most different.
The two that are most different, right? What happens in my head is I go through and I take a look at these means, I'm like, oh, I wonder if these two groups are different, right? But really what you've done is in your head, like that, you've gone through and done all possible comparisons all at once, right? Just in a glance. And what you've done, when it occurs to you to ask whether or not these two groups are different, what you've actually done is cherry pick the two groups that are looking farthest apart, right? And what this does is this dramatically alters your type 1 error, right? It's not just like you randomly selected two means to wonder if they're different. You've gone through, run all possible comparisons, and then gone through and selected the ones that seem the farthest apart, okay? And so what happens then, Tukey then starts to account for and starts to increase the threshold. The classic Tukey procedure starts to increase the threshold for claiming statistical significance or claiming an effect based on how far apart those means are, okay? So with Tukey, what we would do from a classic approach is we would order our cell means. Let's say I've got a one-way ANOVA, 5 levels on my factor, right? I've got an independent variable with 5 levels, 5 conditions. What I would do is I would take those means of each one of those conditions and I would order them from smallest to largest. Okay, so here we've got group 1, 2, 3, 4, 5. Okay, and let's say that this is using a design where I have 8 people per cell. My degrees of freedom error for my overall ANOVA table are 35, and my mean squared error for my overall ANOVA table is 32. Okay, I would lay these out. Okay, and then what I'm going to do is I'm going to determine the number of steps between the means that I want to compare. So if I'm comparing group 1 and group 2, okay, we're going to call that 2 steps. We've got 1, 2. Okay, so we would set R equal to 2 for this. If I want to compare 4 and 29, Danielle, if this is what you're looking at, probably the one that you're most keyed in on because they're the most different. Well, now that's different. My R now is 5. I've got 1, 2, 3, 4, 5. I've got 5 steps with that. So with this, my R is now 5. All right. And so what I would then do is go through for each one of these comparisons. If I wanted to do both of these, and with because it's a post hoc comparison, I would do yikes. I got 10 different pairwise comparisons, I think, in this set of means, right? What I would do for each one of these is I would go through and calculate a Q statistic for each one of these comparisons, right? Here I've got Q R sub 5 because this is the number of things across, right? Because I'm taking 4 and 29, so I've got that divided by my mean squared error for my ANOVA table divided by the number of people in my cell, which gives me a Q statistic of 12.5, okay? And then what I would do is I would go to my Tukey table, my Q table, my studentized range table, and I would go through and find the critical value for alpha equal 0.05, degrees of freedom 35, with R equals to 5, right? And so I would go on that table, figure out where that was, and find out that my Q critical is going to be 4.07. So what I would then do is I would compare 12.5 to my critical value. My test statistic is clearly sort of exceeds sort of my critical value. And so what I would do is then I would claim evidence for an effect. I would reject the null hypothesis of no difference for that individual comparison based on Tukey less than, with Tukey at alpha less than 0.05. In the traditional approach, you don't get a specific p-value for that because it's just like, here's the threshold. If you're below it, it's just Tukey less than 0.05 type of approach. Now, SPSS and sort of modern computational like statistical programs will actually give you a p-value, but from the traditional approach, this is kind of what we would do. Yeah.
On the Q table that we have, it doesn't have 35 degrees of freedom. Do you just kind of
get online and you would say critical Q value or something like that, and it'll ask you to put in the degrees of freedom and your R, and I'll just tell you. Okay, so with a traditional approach to Q, what we would do is we would go through and run all 10 of these comparisons. We got 1 versus 2, 1 versus 3, 1 versus 4, 1 versus 5, 2, 3, 2, 4, 2, 5, 3, 4, 3, 5, 4, 5. That's a lot, right? But from a traditional Q standpoint, what the Tukey standpoint, what we would do is each one of those comparisons would have a different critical value, right? Because here, if we're comparing 1 versus 2, now my Q critical is going to be based on alpha 0.05 degrees of freedom 35, but R equals 2, right? And so what we've got is kind of an adaptive criteria for depending on how far these means are apart. So what I'm doing, Danielle, is I'm getting penalized. If I go through and I cherry pick the biggest ones, I got to pay extra money for that, right? If I'm going through and comparing these ones that are close together, that's going to be a lower critical value and sort of more likely that I'm going to go through and find evidence for an effect. You'll kind of get the basic idea of this. All right. So this is kind of how our Tukey procedure works. But what we can do is, because if we understand kind of what's going on, we can harness the power of Tukey and bend it to our will. Okay. What I can do instead, if I don't want to screw around with Q tables and those types of things, what I can do is I can just determine my critical T value necessary to claim evidence for an effect. Okay. Remember that Q and T are directly related to one another, right? So let's say I've got an ANOVA, 6 levels of factor. I got a big one-way ANOVA. I got degrees of freedom error is 47, right? So let's say if I want to compare the two groups with that are the farthest apart, right? The most extreme critical value I'll get with Tukey. I'll say my Q critical is going to be 4.32 with alpha 0.05, R equals 6 degrees of freedom 47. So I go to my table or my calculator, find out and get my critical value for that Tukey. But because I know that Tukey has a direct relation with Q, what I can do is I can take that Q value and turn it into a T critical, right? So if I take my T critical or my Q critical value and just divide it by the square root of 2, it's going to give me a T critical of 2.99. Okay. Now note that it just my T critical for 47 degrees of freedom, if I'm just running off my T test or off my T table, my T critical is actually 2.02. Why am I seeing a difference here in terms of what I would get from just my T table versus what I got when I translated that Q statistic over? Anything, Olivia? Why for this post hoc procedure would I get a more stringent critical value relative to what I would just pull off on the T?
Say it louder.
I don't know.
I told you, like, I don't know is the only wrong answer. Like, what are we trying to do with these post hoc procedures? Like, what's the whole reason we're doing them in the first place? Well, not to increase power,
See where the difference lies.
to see where differences are, but why? So if I just want to know what differences are, why don't I just go through and test the hell out of whatever I want to, just with T-tests all day long, right?
More error.
Right. So what am I doing to try and control for that error?
You're being more conservative.
Yeah, making it more conservative, right? So what we've got here, if I were to just compare two groups with these degrees of freedom, with just a regular T-test, my critical value would be 2.02. But what we're seeing is the difference when I take my Q statistic and transfer it over to a T, I'm seeing a much more stringent value here. That's because I'm controlling for 6 total means, which is going to be 15 pairwise comparisons. And so what we see is a much more stringent critical value. Even when you switch it over to a T, this is reflecting that additional control for multiple pairwise comparisons, okay? But if I wanted to do that, once I do, I get a critical T value. Now I can just run independent sample T tests till the cows come home, as the kids say. And anything that gets me a test statistic that's greater than 2.9, I can claim as evidence for an effect with my Tukey with alpha equal 0.05, okay? People kind of see what we're doing here with this. Now, the only asterisk here is that if I go through and I do this, the thing is that the T-tests that I'm going through and I'm running, just like our regular old T-tests, those aren't using the same formula. That's not pulling information from my overall ANOVA, right? I'm not pulling out my mean squared error, stuff like that from the overall ANOVA, right? So that T statistic I'm going to get from our routine just T-test stuff is going to be a little bit different than the T-test or the value that I would have gotten if I were to use the mean squared error for my variance estimate. So there's a little bit of a difference here. But if I've got something that's got like kind of a really kind of unbalanced design, I violated homogeneity of variance and stuff like that, this might be a better way to go, right? So it's not a precise one-to-one thing, but I can kind of use this as a way to go through and use Tukey procedures to go through and kind of correct for inflation just because I'm giving myself a more conservative test. This will start to come in when we get into our factorial designs. Okay, but do people see how we're using this? Okay, we just take our Tukey Q or our Q critical for our most stringent test, turning that into a T value, and then I'm just running T tests, and that's my new critical value that I have to exceed.
So you're saying any pairwise comparison, so if we, I don't know, it's a dumb question, but if you wanted to compare different. I don't know how to word it, never mind.
Okay, hold on to that because we're gonna get into some variations on this. Okay. Other thing we can do, because we have command of algebra, is we can simply go through it and take our Q statistic and determine how much of a difference do I need to see in my means before I can just claim an effect, okay? So here, let's say that I find a Q critical of 4.23, given alpha 0.5, R equals 6, degrees of freedom 42, and let's say my mean squared error is 32 here, okay? So again, I've got a pretty big one-way ANOVA, 6 levels to my grouping factor. So I just want to go through, and maybe I wanted to run a bunch of just make SPSS turn out a bunch of stuff. What I might do, if I know that Q is difference in my means over the square root of my mean squared error over my cell size. Well, if I can just sort of rearrange this a little bit, I know that the difference that would be associated with my Q or an effect with Q is going to be equal to Q times the mean squared error over N. So I'm just using algebra to adjust this around. And then I can just solve for my difference here, right? If I do that, so I know my Q critical is 4.32, mean square is 38 or 32. I've got 8 people per cell. If I go through and solve for that, it gives me a difference of 8.46. Now what I can do is I can just go through and take a look at the difference in terms of my means, any mean difference between any two groups that exceeds 8.46, I can claim as different with Tukey alpha less than 0.05. Okay. So these, if I do sort of the regular Tukey, if I do sort of translate things over to a Q or a T statistic, if I just look at difference in means, it's all the same stuff. It's all the same information. I mean, this is a little bit different if I just fall back on just like straight up raw T tests, but functionally I'm just taking this and using this to give me different looks depending on how I want to go through and look at stuff if I'm working this out again. Okay. Now for our one-way tests, you won't have to do this by hand because the computer will do it for you, but you're going to run into situations sometimes where the computer's not going to do it for you right. They'll do something for you, but it's not going to give you the exact corrections that you want. So knowing how to go through and manipulate this, manually go through and do these things can be pretty beneficial. Okay. Questions about this? All right. So going through the different versions of Tukey. Okay. Tukey's honestly significant difference. Tukey HSD. This is like the granddaddy. Like Tukey, like this is the Tukey we see. If you see someone talk about Tukey, they're probably talking about Tukey HSD. Okay, with Tukey HSD, what Tukey HSD does is it evaluates all pairwise contrasts at the maximum value of QR. Okay, so Kate, this is circling back to that QR piece of things. If I'm taking the traditional Tukey approach, what I would do is I would compare each one of those means with a different R value. So that with the means that are closer together would have a smaller critical value. The ones that are farther apart would have a larger critical value. Tukey HSD, everything's at the max level. What we do is we just set that R to a constant for this set of comparisons. And so, for example, if we had an ANOVA with 5 levels, all comparisons would be treated as if they were 5 steps apart. Okay. And what it does functionally is it goes through and it fixes your set of comparisons to account for all possible pairwise comparisons. Okay. This is an important equation to remember if you want to know the number of unique comparisons. That's just your number of levels times the number of levels minus 1 divided by 2. That's going to tell you how many comparisons you have there, right? So if I've got 5 levels, that's 5 times 4 divided by 2 is 10, right? So if I got 5 levels, I've got 10 10 possible comparisons that I can make, okay? We start to think about this. If I just want to go through and jump in the middle of a post hoc test, now all of a sudden I have 10 pairwise comparisons to address. That seems like a lot, right? And who knows what sort of random stuff's gonna pop up, right? But if I run them, now I have to report them, now I have to talk about them. And maybe some of those aren't actually things that are really all that interesting, or if they are different, I'm not sure why, because I don't have a good conceptual or theoretical reason for why those things would be different. Now all of a sudden I'm kind of in a bind because now I have to get creative in my head and talk about why these ones popped and that one didn't and so on and so forth, okay? So we just want to be very careful before we jump into this stuff. Jalen, did you have a question?
Yeah, sorry, could you just say the FWE, like what does that acronym stand for?
Family-wise error,
Okay.
family-wise error, right? So remember, family-wise error is bound by alpha and the number of comparisons times alpha, right? So it's that type 1 error inflation that we get with the one. All right. So again, what I can do is if I'm wanting to take any HSD approach, I can take my pairwise comparisons and I can look at those and I can calculate just a Q statistic for all comparisons with just R set to 5 for everything, right? I could calculate a T critical if I just want to go through and run a bunch of independent sample T tests and just compare the test statistic with T critical based on that I got from my Q critical and just kind of transferred that over. Or I could go through and just compare my minimum difference between my means for based on a Q critical with what my max are, right? So all those sort of adjustments or sort of different variations, we can all do that with our HSD. You're just setting R as constant for all comparisons. You know,
Are all 3 of those functionally the same?
yeah, they're all functionally the same. Yeah. Again, this T is a little bit different because the T that you would get if you were to calculate a Q statistic, you're just using a different variance estimate, right? Which if you haven't violated your homogeneity variance, shouldn't be too big of a deal. But if you have, then it could become a big deal. And so then we'd probably want to go through and you could do this. T is going to be a more conservative approach to this, but we would want to sort of think carefully about how we wanted to manage that. Questions about 2Key HSD? Okay. Benefits of 2Key, honestly, significant difference. One of the most popular testing procedures, if you someone just talk about 2Key, they're probably talking about HSD. There's lots of different 2Key procedures. This one's the most common, good protection against type 1 error. But again, drawbacks, I'm going to lose power in cases where all pairwise contrasts aren't interesting or meaningful, okay? Basically, 2Key HSD is going to give you comparisons whether you're interested in them or not. So it's easy. On the front end, I can just be like, well, I just want to do a 2Key post hoc, right? Problem is if I don't care about a lot of those comparisons, I'm still getting charged for those, and that's going to tax my power, right? And so if I'm in a situation where it truly is an exploratory study, no one's ever done this, I kind of have a general idea of some stuff that might be going on, but I don't know. Let's just see what's different. Then this is a procedure that you can use, but just know that for all those comparisons that really aren't all that interesting or meaningful, you're still getting charged for those, which raises the bar on all of your test statistics, okay? So you just want to be very careful when you're approaching this, given that we live in a world where we make yes/no decisions based on an arbitrary p-value, okay? Questions about this?
So then for this, would you say something too, like that this is a more conservative test?
Well, it's not as, they can get more conservative, right? So if you're doing just a straight up, like, and you're fine and sort of, this is the thing, you can do whatever you want, so long as you're going in there with eyes open and knowing exactly what I'm doing. Like, yes, I'm making an active choice, knowing that if I go this approach or take this approach, it's going to cost me power. But I think given the circumstances, this is my best approach. This 2Key is HSD is a pretty good one to use. Some variations on 2Key, okay? If I have unequal samples, then what we get into is an adjustment here known as 2Key Kramer. 2Key Kramer is the default in SPSS. If you just get 2Key HSD, it's actually 2Key Kramer. It's just adjusting for differences in cell sizes, okay? So again, we're gonna talk about approaches to take with balanced designs and unbalanced designs. If something's relatively close, like we're using balance with a little bit of leeway, like, I mean, mathematically, if you don't have exactly the same number of people in each cell, then you have to change your formula to account for differences, even if you have a difference, if it's a difference of 1 per cell. If I'm talking about, hey, this isn't good for unbalanced designs, I'm not talking about like anything that's not exactly the same thing. It's when you start to get disproportionate representation across your groups. But anytime you have unequal samples, what we're gonna do is we're gonna roll into a Tukey-Kramer. And then you also have what's known as a Games Howl. Games Howl is a version of Tukey. What we're doing is we're just accounting for unequal samples and unequal variances here, okay? So again, with Games Howl, differences in all pairwise comparisons are getting compared against a critical value W, right? It's kind of an analog of Q. But what this is doing is it's taking kind of the same thing as that Behrens-Fisher approach with our independent sample t-tests, right? And it's just going through and making an adjustment on that degrees of freedom number to go through and give you adjusted tests, right? Again, the idea here is that the distribution of my test statistic falls on it is part of the T family. I just don't know exactly what member of the T family it is. It's not the one that it should be because I've got violations of homogeneity of variance. It's still a T distribution. I just don't know which one. And so what we're going to do is we're going to make some adjustments on that degrees of freedom to try and pick an appropriate distribution to fall on. Okay. So if you've got cases with unequal variances and unequal samples, this is definitely probably your best bet here. Okay. And it's easy to go through and request with SPSS. If you've got any concern about violation of homogeneity of variance, this is a fine one to drop back on.
So if you do violate those assumptions, you would recommend using that?
Yeah. As we go through all of our ANOVA stuff and our repeated measures ANOVA stuff at the end of next semester, whether or not I violate that homogeneity of variance assumption and so the number of people that balance in my design, those are kind of two big pieces of information that start to shift sort of what approach I decide to take. Okay, so Haley, this is functionally just the same thing when we run our t-test. We have homogeneity of variance, equal variance is assumed, equal variance is not assumed. This is just the analog of equal variance is not assumed with this one. Okay.
So if sorry, I just want to make sure that I'm understanding. So if we do violate those assumptions, like with the beans, that's indicating that we also have like unequal variance. Okay.
But the thing is, it can get tricky here, right? Because you could have two tests or a comparison that compares groups 1 and 2. Groups 1 and 2 might have very similar variances. Maybe it's group 3 and 4 that are way out of bounds, bigger or smaller, right? What Games Howl is doing is saying, okay, we're just going to correct for that. But with all of these, you're not getting one test, you're getting the whole list of tests with these, right? So it's just going through and accounting for that. So other PSYC procedures, Newman-Cool's test, okay? This is what we kind of talked about as the classic Tukey approach. Newman-Cool's is going to still use our studentized table here, our Q table, but it's going to change that R for individual comparisons. So as those means get farther apart, it's going to increase, the R is going to increase. It's going to give you more stringent critical tests there, okay? So more powerful than HSD, but less control over type 1 error. And again, this is assuming a balanced design, right? So if you're a couple people off sort of across the thing, or even a handful proportionally, if it's wildly different, this is probably not an appropriate approach to take. And you could talk about Newman-Cool's, but like conventionally, people are going to expect you to use HSD. So it's there, it's something that is out there as a tool, but you don't see it quite as much. Chaffee's test based on Tukey, but here what we do is we correct for all possible comparisons, okay? So not just all pairwise comparisons, all possible comparisons that could be made. And so what ends up happening is we have an extremely conservative test, not recommended for pairwise comparisons, right? Because if what you want to do is just compare all pairwise comparisons, back I'm going to use a Chaffee, Because it has a thing that sounds French and fancy, right? What you're doing is not only are you controlling for the tests that you're running and reporting or controlling for other possible, it just makes it extremely conservative. So unless you have a very good reason for wanting to be very conservative with your tests and have made that a priori, what you don't want to do is go through and take a look, run your post hoc tests. And then all the ones that you want to pop up as are all p less than 0.001, and then decide that like, oh man, I'm gonna do Chaffee. Well, you can't do Chaffee after you already knew that sort of it's not gonna make a difference, right? Which happens sometimes in review, right? Like you go through and run your stuff and people like you need to use a bond for only correction. All right, I know it doesn't make any difference from what I wanted. So cool story, bro. I guess whatever you want me to do with it. Like I don't want to do it because of these reasons, but if you're gonna be a stickler, right? With all of these procedures, you want to make a decision before you actually go through and look at these, because then doing it after, everything's out the window. Okay. Done its test. This is cool. What it does is it compares if you've got a design where you have a control group, and then a number of different experimental groups. So Gabe, let's say you're running a study, true sort of nice experiment, right? You randomize people to control group and then sort of manipulation 1, manipulation 2, manipulation 3. And what you're really interested in is comparing those 3 manipulations against that control group. Dunnage could be the test for you, okay? So what it's gonna do is it's gonna go through, use a critical value based on a different table. And what it's gonna do is it's gonna give you, if you've got a control and then 3 experimental groups, it's just gonna give you comparisons of those 3 against the reference group. So if you've got a design that pulls for that, a really nice way to go through and do this again, it's sort of assuming a balanced design, but a nice way to go through and make those comparisons. If comparing experimental 1 and 2 and 1 and 3 and 2 and 3 isn't something that's relevant or interesting for your design, Dunnage is a good way to go. All right, questions on this? All right, let's go through, open up your SPSS file here. And so we'll just go through quick and show you how to pull these up. So we've got, in this example, we say that people diagnosed with chronic pain may have different profiles of coping, okay? So if we take a group of people who have chronic pain, there may be differences in terms of how people go through and manage and cope with that condition. So what we're interested in is looking at the relation between coping profiles and trait level of anxiety. Okay, so our grouping factor here is pain profiles, right? And our outcome variable is trait anxiety. Okay, and so we're looking at this. So we've got individuals who have been in motor vehicle accidents, who are experiencing chronic pain. We've gone through and measured their pain coping profiles, and then just wanting to look at differences across those differences in trait anxiety across individuals with these types of profiles. Okay. So go through and grab your ANOVA post hoc handout. What we'll be using.
Screening.
No. Just the post hoc test on this. Okay. So what we've got in this set are the variables that we're interested in. We've got participant ID, my trait anxiety, and then my pain code profile. We don't need, for this example, we don't need to worry too much about what the profiles are necessarily, but we've got 5 different profiles. We've got an adaptive profile, an interpersonally distressed profile. This is like sort of using, sort of like eliciting help from other people and sort of like pulling in like social supports to try and manage your pain. Dysfunctional, this is people who may have high levels of impairment and things like that, sort of not coping real well. Hybrid is a combination of 2 profiles, and then other is someone who does it, it's kind of fall into anything. Okay, so what we're gonna do with this is we're gonna go into our data set here. And I'm gonna quick sort that for trait we're not screening anything, so it wouldn't matter. It would just exclude those people anyway, so, but that's all right, I'll go through. Nuke those. So we're gonna go to analyze. Compare means, one-way ANOVA. Okay. So we got trading anxiety as our dependent. Our grouping variable is our profile. What I'm gonna do is I'm gonna go to contrast. And you see, we've got all sorts of different options here that we can go through and take a look at. And if you want to get deep in the weeds, if post hoc tests are your thing, you can go through and explore this stuff. What we're going to do is we're going to go through and request LSD, right? This is Fisher's. This is where we don't even sort of make any sort of comparisons across it, right? And then let me request Tukey, okay? And games howl for unequal variances. Let's do Chaffee and done it. Okay. With done it, what we need to do here, you'll see is we need to decide, and you have to code this appropriately so you can have your first or your last group be your control group. Here, let's make it our first because that's our adaptive group. So we'll just pretend for this, let's say we want to compare everybody else against our adaptive groups, right? Then you can say, do I want a two-sided test? Do I think my other groups will be score less than my control, greater than my control? So you're just going through and clarifying whether you want a one or two-tailed test. Here, we'll just say a two-tailed test. And this will be good, okay? So you're gonna hit continue. Under options, we'll have through descriptives, homogeneity of variance, my Welch test, and request a means plot here. If you continue, I'm gonna hit OK. You can all hit paste. Switch back over here. What we get if we look at our descriptives, so this is a one-way ANOVA with 5 levels to my grouping factor, okay? What you're gonna see is these ANOVA models get really, really quick, really, really fast, all right? So you wanna be very careful in terms of, I poke fun at psych and law in here sometimes. Sometimes the psych and law, sometimes your designs will get very, very large, very, very quickly. And then all of a sudden you're sort of running up against how you're gonna manage a 5-way interaction if something were to come up, right? So this is really thinking about how do we go through and sort of manage and thinking about, yikes, what were to happen if things were to come up, and sort of trying to manage and keep things a little bit smaller. But here we can see even as a 5-way or with 5 levels, we're already starting to get pretty big here, right? So looks like our design is pretty balanced until we get to hybrid, and then that hybrid group is pretty small. So that's something I'm probably going to be thinking about. My cell sizes for this type of test, they're not bad, but I'm still not going to have a ton of power with this, right? I mean, it's fine, it's serviceable, it's not super impressive, but we're okay. The only real concern here is that hybrid group that's quite a bit smaller. Okay, so we go through, take a look at our homogeneity of variance test. Haley, what am I seeing here in terms of homogeneity of variance?
There's a glare. It looks like you're right on the.
Yeah, we're kind of right on the border there, right?
Okay, all better, all fine.
Yeah, I mean, so again, what we want to do is, so yeah, we're 5, 6, so we sort of technically have it, but also recognizing that we've got a big design and not a lot of representation, too much representation in these cells. Now, if I had 100 people in each cell, I'd be like, yeah, cool, I'm good, right? Here, it's kind of trending that way, so I would keep it in the back of my mind. I don't know that I would necessarily go to a Welch test or things along those lines, but I would probably say, I'm not 100% sure. Like I wouldn't bet the house that sort of the variability of state anxiety or trait anxiety is identical across these respective populations. Okay, so just trying to be flexible with this. But again, Hey, what are we getting with our ANOVA model here?
Saying that there is evidence for something going on.
Something's going on, right? It looks like my mean, somewhere in there, I've got at least one mean that's different from at least one other mean, right? So my omnibus test is looking pretty good. So I've got evidence for some difference. And then if I go down through and I take a look at my eta squared, I would say here, based on these data, within this set, coping profile is accounting for about 16.6% of the total variability in trait anxiety, right? Or I could go down here for my omega squared, and I could say, based on the data that I've collected, we would expect coping profile to account for approximately 13.2% of the total variability in trait anxiety within population of accident survivors experiencing chronic pain or something like that. Remember, this is a sample statistic, and this is going to be a population estimate here. Okay, so just noting the difference between those two. Okay. And here is my means based comparison, right? So just eyeballing this, it looks like in terms of trait anxiety, my adaptive copers are pretty low, my dysfunctionals are pretty high, interpersonal distress is up there, hybrid is kind of here and other is kind of down there. So we can see variability in across these means, okay? Now in your handout, I didn't actually include any of the post hoc tests. That's because what ends up happening is the post hoc tests, particularly if you ask for a whole bunch, you get a whole bunch of stuff, okay? So let's go through and take a look at this. If you have this up on your own screen, I know it's going to be hard to see there. But what we've got first is we've got two, okay? Now what you'll notice in these tables is a whole lot of redundancy, okay? Here I've got adaptive versus interpersonal, adaptive dysfunctional, adaptive hybrid, adaptive other. And then we just do the same thing over and over again. It's just the same comparisons, just configured differently, right? But we have an estimate of our difference between our means, right? Our standard error, our p-values, and then our confidence bounds, okay? So here we have Tukey. Here we have Chaffee, right? Here we have our Fisher's least significant difference. Here we have our Games Howell, and down here we have our Dunnett's test, okay? And we'll see here Dunnett is limited to adaptive versus interpersonal, adaptive dysfunctional, adaptive hybrid, adaptive other, right? If we're comparing this as our control group, okay? But for all of these, a metric of your difference, your standard error, your p-values, and then your confidence bounds. So nothing too confusing going on there based on things that you've already done, okay? The problem is looking at this turns into a mess, right? Is it just a whole bunch of redundancy, and it's you know, normally you're not going to ask for 7 different post hoc tests. You're going to sort of know which one you want to just request those, but there's still, even if we just look at even if we just take LSD, there's just a lot of redundancy there, okay? So for something like this, to try and figure out how do I make sense of this, or what do I do with this in terms of, for me, trying to analyze and see what's happening, this is where we have to get a little bit creative and start making our own use of tables and things along those lines. For this, what I've got here is I just went through and just created a table like, okay, how do I go through and present this? Like thinking about, and so you notice on problem sets, I'm giving you bonus points for stuff. It's because you and your group made my life and Matt's life easier by going through and laying things out so we can go through and find things, and you're using sort of flexible interpretations. You're just doing a really nice job with stuff, right? Here would be something that would be really nice to see, right? I don't want to see a giant printout of everything that you've got. What I want to see is you've gone through and synthesized this. And so what I've done here is go say, okay, the comparisons are all going to be the same across each one of these different groups. Let's go through and plot out the difference between Fisher's, Tukey, Games House, Chaffee, and Dunnett, and then just kind of highlight so which ones popped up as evidence for an effect. Okay. So Allison, if I'm going through and I'm taking a look at this, what are we seeing based on the comparison of these different post hoc procedures?
Well, it looks like you highlighted the ones that are less than 0.05.
What's that?
It looks like you highlighted the ones that are
Yeah.
less than 0.05.
Yeah.
So like there's evidence for a difference between like adaptive and interpersonal, adaptive and dysfunctional and other.
Yeah, right. So if I'm looking at these different procedures, anything you're noticing similar or different about these?
For what you're asking, like
Am I getting the same effects for all procedures?
not all, but like most, like the ones that are coming up as different as different in multiple different tests.
Yeah, right. So again, if we look here at our output, we can start to see how we're getting some differences in terms of how conservative some of these tests are, right? Our Fishers we know is the least conservative. It's the most liberal, right? And here we've got differences in interpersonal adaptive and interpersonal dysfunctional and then dysfunctional and other, right? And we've got pretty small p values across these. With Tukey, now we are adding a correction. We're still getting the same patterns, but we're seeing the p values are smaller, or excuse me, larger, because what we've got is a more stringent criteria. So we can start to see this. When you get into Chaffee, remember we talked about Chaffee as being way too conservative for what you want. You're putting forth way too much correction. Here we've only got one effect that's come up. Games Howell, what ends up happening, this is kind of interesting, right? We go from our Fishers where we have what we'd say is pretty clear evidence for an effect. By the time we get to Games Howell, that's a Tukey with a correction for unequal variances, right? Which we didn't have evidence for, but completely didn't rule out. Now we see adaptive interpersonal just kind of tipped over on the other side, right? So you can start to see how this the different procedures start to change the specific effects that start to come up with this stuff. Yeah, Jim.
How do we highlight stuff on SPSS? Isn't there a way to do that?
Just double click on the graph. And then,
In SPSS,
and then you just slide over to you gotta make your window bigger. And then double click or just click on whatever box you want and then go up that little white box over. Right there. And then you click what color you want.
Oh, okay.
And then.
so what I would say is make use of Excel in terms of just like dropping things into tables that you can go through and create and sort of make sense on your own and sort of put together, right? And so with this, I could then also add in columns for effect sizes or confidence bounds. They're sort of playing around with this. Part of this is just being creative as scientists, thinking about like, okay, I've ran my analyses and here's what I think it says. How do I communicate that effectively to other people? Okay. So, but can people kind of see what happens depending on what procedure we select? So we start to get a little bit different things. Here, I would say adaptive dysfunctional comparison is probably like that's probably the thing that's kind of the most consistent. And then we get adaptive interpersonal is probably reliable-ish. Yeah.
So, but when people do post hoc analysis, they're not running all
No, they're not.
5 of these, okay?
They're not. But what I want to know is that you know how to do these and sort of the differences and stuff like that. And so just going through and doing this and thinking. Now, I'm not going to have you write interpretations for all of those, right? What I will have you do is sort of like think about what's going on with the problem and choose one of these and tell me why you think it's the best and then sort of make your interpretations based on that. Okay. Questions about this? Okay. Last thing. Okay, again, thinking about how do I go through and communicate information to people? We've got a number of different comparisons. Again, if I've got 5 comparisons, or if I've got 5 levels, that's 10 different possible pairwise comparisons that could be done, right? Trying to think about like, how do I go through and communicate this? How do I talk about this? How do I show people these are the ones that are really different than other things? What I've given you this ESCI plot. This is a really slick spreadsheet that Cumming and Fitch put out. If you go down here on the tabs, it just goes through and talks about sort of different ways to go through and set up. Like if I go through and I can enter a correlation in my sample size, it will just measure automatically confidence bounds around that correlation, right? Same thing if I have differences.
Where is this at? Is that in
Portions.
Bermuda?
Yep. So differences in sort of confidence bounds around means, paired means. So it's just a really, really cool way to go through and generate a spreadsheet that's just set up to generate confidence bounds around point estimates of stuff. So if you play around with the tabs, look around the tabs.
Sooner.
Right? So but here, if you go to this known limits right here at the end, here I can just go through and punch in whatever my point estimate is and my upper and lower bounds. And it's just going to give me a little plot that goes through this. And so in situations like this, if I have a number of means that I'm wanting to compare and really kind of communicate to my audience, like this is kind of what's happening. These are the things that's different than other things. This is a nice way to go through. I've used this in several publications. It's started to become my go-to thing, either within the manuscript or as an appendix. I just go through, literally enter things into this and then fool around with the display a little bit so that it looks like something that would show up in a publication, and then I just kind of drop it in there, right? It's a really, really, really slick way to go through and say, if I'm trying to make a number of comparisons or look at things across different samples back, no, this is how things are different, or this is stuff that's maybe not exactly the same. So it's a nice tool to use. So, and this is what I'll have you do in this set, have you go through and plot some stuff out, kind of use that to augment your interpretations with stuff. So graphs are fantastic. We should use them more often than we do. So, all right. So question is, which one of these procedures is best? Okay. Depends on your hypotheses, your design, your aim, what you're trying to do. There is no one best. If someone's like, oh, you always have to use this, this is the best spec, that's not right. And it requires you to go through and think about what are you trying to do. Okay. Again, if you have a well-constructed study and you know ahead of time, you've got a good conceptual background, you know which comparisons in this ANOVA are going to be the ones that are most important for making your arguments or testing your theory. Independent sample t-tests or and sort of consider Bonferroni, Dunsidak with planned comparisons. If you've just got a handful of these, just falling back on a t-test is completely fine, right? To say, hey, I've got a set of 3 comparisons. I'm just going to go through and fall back just to be conservative. I'm just going to run independent sample t-tests within the comparisons that I want to look at and that I think are most important. Maybe I have a Dunsidak correction, so I adjust the alpha on that a little bit just to sort of make sure that I'm accounting for stuff, right? Completely fine, okay? If I plan my tests in advance, I'm interested in complex comparisons, right? I'm saying that, well, I think this group that I'm most interested in is going to have higher scores than the combination of these 3 other groups. And then I think these 2 are going to be different than these 2. That's when we're talking about our linear contrasts. This can be a really, really, really effective way to start to reduce the number of comparisons that you're doing. Instead of, oh, well, I think that 1 is different than 2 and 3 is different than 2 and 4 is different than 2. If they're all different than 2, just say like the combination of these versus 2, right? I don't have to go through and step each one of those out individually if there's not a real reason to do that, right? So again, these linear contrasts are really fantastic. And again, we can consider making a small correction with Bonferroni Dunsidak if you just got a small set of comparisons. If I've got a large number of exploratory tests, post hoc tests, I'm just like, I don't know, I'm just going to see what happens. Tukey or some variant is probably going to be the most recognized approach. no one's probably gonna give you any garbage if you like, and then I too corrected for things, just make sure that you're recognizing potential impacts with violations of homogeneity difference and stuff like that. Make sure you're being mindful and intentional about choosing sort of which one of those you go with.
You
Yeah.
said SPSS automatically does Tukey with
Tukey
the
Kramer,
grader.
Yeah, it'll make that adjustment automatically, so. Questions? Perfect, okay, cool. Let's go through, take a break. Yeah, we'll come back at we'll call it 3:35.
Check on.
Oh, yeah.
Yeah.
Hey, guys. Have delicious.
Oh.
She's also
All right, folks, recording, I'm mic'd up, I think we're good to go here. So just wanted to give you, again, I talked about, that ESKI, Excel sheet to give you examples like, so this is, paper like a psychometric paper where we're looking at, correlations. Yeah. So each one of these point estimates is a correlation and then confidence bounds around that, right? So for we've got one scale and then two scale across different samples that we've got. So a nice way to go through and say, okay, like what types of things are similar or different. So it's just a nice way to go through and you can modify this to set things up to make some of those comparisons. Same thing, here's a different paper where I went through and played around with some color. Again, this is just looking at correlations across 3 different samples, right? So a really nice way to say, if I'm looking at a correlation table, I'm like, oh, well, that number is not exactly the same as that number. We go through and put confidence bounds around it and say like, oh yeah, it's not the exact same number, but this is very clearly having the same zero correlation with biological sex across all of these samples, right? And here, maybe we see, okay, that correlation is these ones are very close to 0 and this one's maybe not, but there's still a lot of overlap, right? So being able to go through and visually use this to go through and take a look to see, sort of make arguments about what things are looking like. So again, here, like in this top panel, across these 2 samples, these point estimates are all pretty similar, right? But if we go down through and we take a look at this group right here, we've got this one's okay, these ones are a little bit different, but we've got very clearly something different going on right there, right? So just thinking about how to use sort of figures creatively to go through and communicate some of the stuff that's going on. So just want to give you some applied examples of how I've gone through and used it. It's a pretty slick sheet, so.
When you changed the colors, did you just like copy over that output into
Yeah, I just,
your own thing? And
yeah, I
then
just
color?
pasted it in there and then fooled around with
Okay.
taking things off and, yeah.
Neato.
I'm an Excel wizard, making research art, so. talk to me if you have any issues.
Hey,
You'll get
mine
there.
was beautiful. My Excel sheet always had 5 is beautiful.
Complained
It
about
was
it
very
the whole
beautiful.
time.
I complain about it, but you know, I complain stuff, but I still do it.
You're learning
I'm
lots.
that kind of person. I complain, but I do it. There you go.
People love those kind of people, so good. All right, so we're gonna switch over into.
Oh, cute.
Not a permanent character, fly, believe me. All right, so you're gonna switch over to Factorial ANOVA. This is our last set of slides, okay? So,
Forever?
this is not forever.
Oh.
This class, we got a whole new deck of them, so like, you got the sequel.
Wait, in this
153.
class though?
Yeah.
This is our last set?
Yeah, this is our last set of slides.
Oh,
Yeah, right? We're here at the end.
let's get crazy.
I know, right? It's exciting.
Take our time.
All right. Here's the thing though. We're gonna go through, take Factorial ANOVA. This is gonna get a little bit. It gets a little bit complicated, okay? So, but we're not doing anything that's too new. We're just kind of adding on, and this is how all of our analyses go, right? So long as we have foundations down and understand things really well. So we're just kind of adding on that and building on that. And our factorial designs, this is kind of the bread and butter of a huge portion of our psychological or our work in psychology. This is kind of the workhorse of a lot of our research. Okay, so we're going to start with the conceptual overview, talk about main effects and interactions, talk about how we calculate and partition variability in factorial ANOVA, talk about effect sizes, a GLM approach real quickly, although that's not important really for this class necessarily, and then the follow-up tests. That's where things get a little confusing. You gotta make sure you got a good game plan with this. Okay, so up to this point, what we've done is we've been working with one-way ANOVA to look at the relation of some categorical variable, some grouping variable with some continuous outcome. Okay, and that's worked really nice in those settings. Okay, and we can think about this ANOVA as an extension of our t-test to compare 3 or more different groups. Okay, and again, we had talked about t-test as actually being a special case of ANOVA. If I have just 2 groups, I can run that in an ANOVA, it's just fine. Okay, so if Abby had an ANOVA, or I had 2 groups and I ran it in an ANOVA and I got an omnibus effect, do I need to do follow-up tests with that?
No,
No, why not?
because there's only 2 groups.
There's only 2 groups. My omnibus test says there's a difference in some group in there somewhere, whether you've only got 2 groups, right? So you just look at the F test, and if it's giving you evidence for an effect, and you just look at which group is higher, and then you're like, this one's higher than that one, right? That's all you need to do. But just recognizing that that t-test is mathematically equivalent to a special case of ANOVA, right? But what happens if we've gotten interested in the effect of multiple factors on an outcome, right? There's nothing in psychology that's determined by one thing, right? Quite the contrary. There's always so many different, and when I was funded, some of this questions from Psych and Law, when people are getting very ambitious about their designs, it's only because there are just so many different things that can go through. We want to account for participant sex, and we want to account for this bias and sort of these types of things. But as we start getting in, there's just lots and lots of things that can go through, and we know we'll go through and influence behavior, right? So we want to go through and maybe try and maybe not account for all of them, but at least some of them, right? So maybe what we have is a situation where I'm interested in the effect of multiple factors on some continuous outcome, right? I could conduct a bunch of one-way ANOVAs, right? So let's say I've got, well, I want to look at sort of this experimental condition and this experimental condition, and then some sort of naturally occurring grouping variable on some outcome, right? Well, I could run my first grouping variable, run a one-way ANOVA there, and I could run another one with my second grouping variable, another one with my third variable, right? I could certainly do that, right? But we get back into that same situation that we had with why don't we just run a bunch of t-tests? Well, one, we've got alpha inflation, okay? But the big thing is if I just run multiple one-way ANOVAs, what I might do is I may miss important combinations of factors, right? So maybe it's not just this factor independently. Maybe it's the combination of these two that's starting to go through and impact something, right? Maybe it's not just this condition on my outcome, but this condition. But if I cross those conditions, maybe there's something about that combination of conditions that then starts to impact things, right? If I'm running just a series of one-way ANOVA, I can't test that. I can't test the combination of things, okay? So this is where we start to get into the true benefits of our factorial design, okay? A factorial ANOVA is a procedure where we start to incorporate 2 or more factors into the same analysis. What we get with this is we get an analysis that's more efficient than multiple one-way ANOVAs. We avoid our type 2, type 1 error. And what we get is something that requires fewer subjects or participants than multiple ANOVAs and still get some comparable power. So we've got some benefits there, okay? We get a greater generalization, okay? Again, because if I'm finding differences within a group that are if I find deviations from the mean within a group, what do we call that?
It's error.
Yeah, you're exactly right. It's within group error, right? It's something that's shout from the rooftops, yeah, right? And that's not to say it's random error. It could be due to something. But if we haven't included it in our model, then it's by definition error, right? But if we suspect that there might be some reason why things are moving around, maybe we go through and model that. Maybe we include that in, and now all of a sudden it's not error. It's something that we've accounted for, right? And so what we can do is start to look at multiple different factors that might influence behavior, which is going to give us a more generalizable solution, something that fits a little bit better than looking at like, well, is it just this one thing, okay? And so what we can do is we can look at differences across level of a factor in the presence of other types of variables and conditions. Like, okay, so yeah, I'm seeing differences across groups, this group, but what happens if we go through and add this stuff and we still see those differences play out the same way? And here's the thing that's really important. What we can do is we can start to look at the combined effects of multiple factors on some specific outcome of interest, okay? These are going to be our interaction effects. Okay? When we're talking about this, anything that says interaction, anything that says moderation, so that these are all things, conditional effects. These are all terms that we use to talk about when we've got a combination of influences that together work to influence some type of behavior or outcome. And again, just greater overall flexibility with experiments, right? If I don't have to choose the one thing that I want to look at, if I can start looking at a couple different things within the same design, then that starts to become really slick. So thinking about some basic terminology here. If I'm talking about a factorial design, this is a situation where I have every level of one factor paired with every other level of subsequent factors. If it's a full factorial design, I've got all possible combinations of my independent variables linked together here. Really important in terms of notation. Our factorial designs are going to be indicated. We have kind of a specific way of reporting what this is that very efficiently communicates sort of what I've actually got going on. So let's say I've got say that I'm running a 2x3 factorial ANOVA. That says I've got two factors, right? I've got factor A and I've got factor B. Factor A, 2 levels to factor A, factor B, 3 levels to factor B, okay? So being able to look at that and sort of know what that means is extremely helpful for understanding how people have put together their design, what they're actually going through and taking a look at, and how many cells, groups that you should be expecting to see within those analyses. Okay. So Jalen, with this 2x3 factorial design, how many groups are we actually looking at here?
6.
6, right? I'm going to have 6 individual cells that I'm going to go through and be accounting for here, right? So I know going in what to expect, kind of gives me a map and a headspace for anticipating what to see. Okay. Cell, same thing as before. This is just our subsample involved in a specific combination of factors. Thing to remember is each one of these cells represents a unique population. Okay. This is a group of individuals, hypothetical group of individuals who have experienced this cross of X and Y. So each one of these individual cells represents its own population of individuals, okay? So keep that in mind. In factorial designs, what we're gonna have is we're gonna have main effects, okay? Our main effect is gonna refer to differences in means across levels of a given factor collapsing across the other factors, okay? So if I'm looking at, in this 2x3 factorial design, I'm going to get a main effect of factor A and a main effect of factor B. Main effect of factor A says, do I have differences in the levels of factor A ignoring factor B? My main effect of factor B is going to say, do I have differences across levels of factor B ignoring factor A? Okay. So these are our main effects. And then what we're going to have is we're going to have conditional effects. We just call these simple main effects sometimes. What this is going to give us is the effect of one factor on our outcome at one level of a different factor. Here's where we're going to start to get into the stuff that makes factorial ANOVA a little bit tricky. Kind of have to wrap your head around it like a puzzle. What we're saying here is that we've got an effect that's conditioned on another level of on the level of another factor. Okay. So here, if we have a 2x3 design, right? If I'm looking at conditional effects, I would say that the difference between level 1 and level 2 of factor A, right, changes depending on what level of factor B that we're talking about. So at level 1 of factor B, I've got this difference between these two. At level 2 of factor B, I've got this difference. And level 3 of factor B, I've got this difference, right? So if you ask me if we get an interaction effect in the factorial ANOVA, when you say, hey, what's the difference in levels 1 and 2 in factor A? You say, I don't know. Depends on factor B, things start to change around. Okay. And this is where we get into our conditional effects. We're going to go through an example, kind of look at what this looks like from a practical standpoint, so you can kind of see this, but just so that we have some terminology, shared terminology here. Okay. So when we were working on our one-way ANOVA, right? We had talked about this situation where we had people go through and complete some sort of task in rooms of different ambient temperature, right? So we had what was it, like 50, 70, 90 or something like that, or 60, 70, 90, or no, 50, 70, 90. Yeah, that makes sense. Okay. And so it's saying, does ambient temperature impact performance on things, right? But for those of you, who are my folks from the South? They're from the South.
Well, Haiti, south of the US.
That counts. We'll allow it. Right? Does it always just matter what the temperature is? No, right? I will tell you that 20 degrees here in Laramie feels very, very different than 20 degrees in, let's say, Memphis, right? Also, 80 degrees here feels very, very different than 80 degrees in Haiti, right? Because we've got this humidity factor thing going on, right? And so what I might want to know is maybe it's not just temperature that impacts performance, but what about humidity too? Like what if we were going through and accounting for this? And so maybe what I do is I transition away from my one-way ANOVA, where I'm just looking at the impact of temperature on performance, and I switch over into a factorial design where I'm looking at the combination of heat and humidity on performance, okay? So what I've got is an experiment set up where I've got 70, 80, and 90 degree temperature, right? But then I have low and high humidity conditions. So some people are going to be completing our task in low levels of humidity, some people in high levels of humidity, right? And my question is, what are the combined effects of heat and humidity on performance in this situation? Okay. And so what I can do is I can have a number of different questions that I can ask based out of this design. I can say, what's the effective factor A on outcome? Okay, and if we talk about factor A is our humidity, right? What's the effective humidity on performance? What am I talking? What does this question correspond to from the previous slide?
Main effect.
It's a main effect, right? Ignoring temperature. If I just look at people performing low humidity and high humidity, do I see a difference? Okay. I can also ask about the main effect or the effective factor B on outcome. Again, a main effect. Ignoring humidity. Do I see differences in people completing a task at 70, 80, 90 degrees? Okay. And then I have my interaction. What are the combined effective factor A and B on outcome? What's the impact of specific combinations of humidity and temperature on performance? Okay. Here, what we're going to start to get into is maybe it's not just humidity, maybe it's not just temperature, maybe it's the combination of these two that start to produce some different impacts on performance in ways that influence how people are able to go through and complete whatever it is that we're going to go through and ask them to do. These are our interaction effects, and where we start breaking out and comparing these individual cells, these are going to represent our simple main effects. Questions about this? Do people kind of see kind of the logic behind this? All right, so what we have here is a 2x3 ANOVA design. I've got 2 levels of factor A, 3 levels of factor B. I've got a 2x3 twin factors ANOVA. I've got 6 distinct populations here. I've got 6 different groups that are going through with their own mean, their own standard deviation, their own distributions here. Got it? Okay, so think about main effects. All right, so let's say here's my table of my hypothetical study here. I've got 70, 80, 90. I've got low humidity, high humidity. I've got individual means for each one of these conditions. And then what we have here is what we call marginal means, right? We've got the mean at 70 degrees, 80 degrees, 90 degrees, low humidity, high humidity. So when I run this analysis, right, I'm going to get not just one effect, I'm going to get three different effects here. I'm going to have a main effect of humidity. I know hypothesis being that performance at low levels of humidity is equal to performance at high levels of humidity. My alternate hypothesis being that performance at low is not equal to high. Okay, Gabe, where am I seeing my main effects of humidity in this figure or in this graph?
Sorry.
Yeah. Where, if I was looking at that graph, where would I look to see evidence of differences for a main effect of humidity?
Low versus high?
Yeah. Yeah, where would I on this graph here, where would I go through and see that?
Oh. That. Those beam of 80 weeks.
These marginal means right here, right? So again, what we're saying is ignoring and collapsing across temperature, right? Do I see a main effect of humidity? What's performance look like at low versus high? Okay, so I don't care what humidity, I'm collapsing across humidity, or temperature, I'm just looking at humidity, okay? What we do is we look here, our F ratio here is going to be our observed variability across our humidity means over the expected variability of the null hypothesis for trip. I'm also going to have a main effect of temperature, right? My null here is that 70 equals 80 equals 90. My alternate hypothesis is that mean performance differs at least one temperature condition. Haley, where are we seeing differences? Where would we see a main effect of temperature?
Marginal means across the bottom.
Marginal means across the bottom. I don't care what humidity looks like. I'm just looking at 80, 70, or 70, 80, and 90 degree temperatures. Do I see differences here? Right. And so again, I'm going to get an F statistic for my main effective temperature. It's going to look at observed variability across my temperature means over the expected variability of the null hypothesis for true. People see where we're getting our main effects here. Okay. The important thing to remember is that when we're looking at main effects, we're collapsing across the other factors. We're ignoring those, right? We're just saying taken together, right? So this is literally the average of these two. This is literally the average of these two. This is literally the average of these two. It's just collapsing across, ignoring those and just looking at means of everybody who completed at 70, means of everybody who completed at 80, mean of everybody who completed at 90 for temperature, main effective humidity, everybody who completed low, everybody who completed at high. People following this?
I do have a quick question.
Yeah.
When you, just like when you were talking about that, it reminded me of when you mentioned on the previous slide, the 6 different populations. So when we're talking about that in terms of like interpretation, are we saying that like each condition is its own population?
Each condition here, yeah. I mean, so what we would say is, if we say, essentially what we're saying is, what's the effective temperature ignoring humidity, right? So what does performance look like in high humidity performances, and what do temperatures, and what does performance look like in low humidity performances? Okay. Now, when we're going through and screening this, how many different groups will we have when we're screening this? 6, right? But what we're going to do is look at those individual cells and not then add on, well, collapsing, like we're not going to do that. So really your populations are the ones, or your individual cells. Your main effects are just looking at collapsing across some of these populations. All right, so we got our main effects. What we get into now is our interactions. Interactions are awesome. Interactions are the bread and butter of psychological research. If you can find an interaction, there's probably a good chance you can write that up and publish it somewhere. Okay. Problem is sort of making sure you understand what an interaction is, what it means, and how to think about it conceptually. Okay. Our interaction effects are going to indicate variability across our individual cells that exceeds what we would predict from our main effects. Okay. So we're seeing maybe evidence of differences in my main effects What's going on with my interaction is I've got differences in my individual cells that go above and beyond that. So there's demonstrating variability that's not fully accounted for just by my main effects here, okay? And what we would say here is this is a situation where we have an interaction. From a conceptual standpoint, this is maybe sort of one of the most important phrases that and it's gonna keep coming up again and again and again, okay? What we're talking about with an interaction effect is it's saying that the effect of, or the nature of the effect of one factor on an outcome depends upon some second factor, okay? If anybody says, hey, there's an interaction of X and Y on Z, you don't have to know anything else. If someone tells you that there's an interaction of X and Y on Z, you say, okay, what that tells me is that the relation of X on Z is dependent on Y. Or the relation of Y on Z is dependent on X, right? So if you just ask me, if Haley says, hey, Josh, what's the relation between X and Z? I'll be like, I don't know. What's Y? Because I need to know Y, because that changes depending on Y. What's the relation between, what's the difference on levels of X on my outcome? I don't know. I need to know what values are for Y in order to be able to tell you that stuff, right? What we're talking about is conditional effects, where we've gone through, we've got interactions where the effect of one thing on another is dependent on some other variable, okay? So for the current example, some interaction effect would suggest to us that the impact of humidity on performance depends on the temperature. If you say, hey, how does humidity impact performance? I don't know, how hot is it? Because that really starts to depend, right? Or we can flip it around. We can say, what's the impact of temperature on performance? Depends, I don't know, it's how hot is it outside, right? Versus how humid is it, right? If I go through and I'm playing, if it's 90 degrees in Miami versus 90 degrees in Denver, those are very different football games in terms of what it feels like to be out there on the field, right? I have to know what the humidity is looking like, okay? And so again, what I'm gonna get, so I've got my main effective temperature, I've got my main effective humidity, then what I'm also gonna get out of this design is an interaction of humidity and temperature, okay? My null hypothesis here is that the effect of humidity on performance is independent of temperature. Humidity impacts performance irrespective of temperature, doesn't matter. Temperature can be high or low, doesn't matter. It's the same. My alternate hypothesis is that the effect of humidity is going to be dependent on temperature. How hot it is impacts the effect of humidity on someone's performance is going to depend on how hot it is, right? So again, we've got three effects here. We've got a main effect of temperature, got a main effect of humidity, and then we've got the interaction of temperature and humidity. And that interaction is going to be, if that interaction is present, it's saying that there's something going on with that combination that goes above and beyond sort of what we would expect just based on the main effect of the other two factors. Okay, so if we're looking at this situation here, right? We have, what are we seeing here? Are we seeing a main effect of temperature here?
Yes.
Yeah, I would say so, right? We're seeing that as temperature increases, performance decreases. Are we seeing a main effect of humidity? Yeah, it looks like people are performing better in low humidity than high humidity. Are we seeing an interaction of temperature and humidity here? What's that?
Yeah.
Essentially.
Okay, you're saying potentially. Abby, you're saying no, why not?
Cause like when you look with like on the inside cells, like low humidity always has like the higher performance compared to high humidity at
Yeah.
every temperature level.
Yeah, if I go through and I take a look at if I'm just looking at low humidity, as the temperature increases, I got a 5-point decrease, 5-point decrease, right? If I look at high humidity, 5-point decrease, 5-point decrease. If I look this way, we've got a 10-point difference, 10-point difference, 10-point difference. It's all kind of working in the same direction, right? So is there anything going on in these cells that's not already accounted for by the fact that performance decreases as temperature increases and it increases as humidity goes down? So we're just eyeballing this. no reason to expect an interaction sort of in here, right? So we've got a main effective humidity, we've got a main effective temperature, but we're not really seeing any evidence of interaction effect in this. What about this? Yeah, what are you seeing here, Mandy? Mandy, do we have a main effective temperature?
Say that again?
Do we have a main effective temperature? Do we have a main effective humidity?
Yeah.
Yeah. Do we have an interaction of temperature and humidity?
Yeah,
Yeah, why is that? What's happening?
because like as it increases, the mean is like very different between like low and high.
Okay, if I look, probably the easiest way to think about this, if I look at low levels of humidity, performance stays constant. It's the same, right? It doesn't matter if it's 70 degrees, 80 degrees, 90 degrees, it's constant. But at high levels of humidity, now all of a sudden, as my temperature starts to increase, my performance starts to drop off. Okay, or I can look at it this way: at 70 degrees, no difference in low and high. 80 degrees, 10 point difference. 90 degrees, we got a 20-point difference, right? So we've got different things going on. Now, Kate, did my marginal means change at all? No, my marginal means are exactly the same, right? No difference there. But now all of a sudden I've got a pattern of means that's suggesting the presence of an interaction effect. In this situation, I would say, if you say, hey, what's the impact of humidity on performance? Okay, I don't know. You got to tell me how hot it is, right? Or how does temperature impact performance? Depends. Is it humid or is it not humid, right? We've got a dependency going on in there that's not accounted for by our main effects. So these can be kind of tricky to go through an eyeball if you're just looking at means. Anytime you get an interaction, anytime you get an interaction, first thing you do is plot it. Always plot it. Don't try and jump into post hoc tests. Don't sit down, plot these things out. Because when you go through and when you take a look, now all of a sudden it's very, very easy to see whether or not we have an interaction. So this is our first example, right? Low humidity, high humidity, parallel lines. Same thing going on, no difference. Whether I'm high humidity, low humidity, or high humidity, I'm seeing I've got an effective temperature, right? As temperature increases, my performance goes down. As I switch, my low humidity is always better performing than my high humidity, but those main effects are accounted for all the variability that's happening in these data. Here, however, we've got two very different things. We've got lines that aren't parallel. We've got at low levels of humidity, temperature has no impact on performance. But as soon as we bump things up into high humidity, now all of a sudden things are taking a dive. Okay, so plotting these out is the best way to go through and see visually the nature of your interaction. And this is going to help you start thinking about, how do I go through and start to tease this apart? What's the most efficient way of going through and pulling things out with some follow-up tests? Questions about this? Can people kind of see where these interactions are falling? Now, we can also see sort of all sorts of, let's say, these are all nice kind of straight lines in parallel, but they don't need to be. Here, we've got no interactions, right? So we've got differences across factor A are all identical, B's, right? Same thing here, same thing here. It's when we start to get non-parallel plots within our factorial plots here is where we start to say here at B2, A has no impact on our outcome, right? It's all the same. But at B1, A now starts to have an impact. As A increases, my outcome increases. Right here, kind of a nice little cross effect. At B1, performance goes down as A increases. At B2, performance increases as A increases. We've got kind of a different thing going on here. Here we've got a little bit different, kind of one going this way, the other one going this way. We've got differences going on within these that are captured by this interaction. Okay, so always, I cannot, again, Excel is your friend. Just go through, throw up plot out those means, and just pop up an interaction or a plot. You're going to see sort of the nature of that interaction very quickly. All right. We can also represent, and often will, it's a matter of taste, right? But when I'm doing group-based designs, things like this, bar graphs are usually kind of, for a completely between groups design, bar graphs are nice because each one of these bars represents a different kind of group of population. okay? So for our temperature and humidity example, here I've got a simple effect. We're seeing the simple effect of factor A at B1 is the same at B1, B2, B3, right? If I'm looking at comparisons across low and high humidity, the difference is the same as 70, 80, 90 degrees, right? If I go through and plot this, and we'll encourage you for ANOVA group designs to plot these as bar plots, right? But if I draw a point at the top of each one of these bars and draw a line through them, it's going to give me parallel lines. It's the same type of thing. But here, if we go through and plot this, we're seeing something very different. At 70 degrees, there's no difference. At 80 degrees, a little bit of a difference. 90 degrees, pretty big difference. If I draw my lines here, I'm getting crossed lines. You can start to see the interaction effect going on here. Okay. All right. So here's the question. Can or should we interpret main effects in the presence of reliable conditional effects? So if I have an interaction, right, should I be looking at or interpreting any main effects? Thoughts?
I think yes.
Yes. Does anybody disagree?
Maybe.
No, maybe, maybe,
In my,
How about the
I think in
interaction
my previous stats said no. but I
Okay.
don't know.
In your previous stats, right? And this is why I bring it up, because this is the thing, Danielle, and some people would say, like, in the presence of interaction effects, you do not interpret your main effects, right? And why would that be?
Maybe the interaction is saying more than those main effects, because it's
Yeah.
the interaction, I don't know if I'm wrong, but that sounds like mediation. No, how you would moderate it?
Moderation.
My bad, thank you.
Yeah, yeah. Okay, yep, and you're exactly right. And the thing is like, what's the main effect of factor A? Like, well, in the presence of an interaction, I can't tell you that unless I know the level of factor. I can't give you a specific interpretation. Conventionally, what we would say is in the presence of an interaction, we would go through and ignore the main effects, right? Because those main effects are not now main effects, they're conditional effects. Because those specific effects, the specific effect of factor A depends on the level of factor B. So I could make an argument that talking about the main effect of factor A is not important because it really depends on sort of the level of the other factor, right? And so by convention, what you'll see is if I go through and I have a design and I'm saying I'm finding a main effect of factor A, maybe a main effect of factor B in an interaction, what I would do is probably just go through and just say what I found here was evidence of an interaction of A and B on my outcome, saying that differences across levels of factor A are dependent on factor B, or the other way around, they're interchangeable. You can talk about it however it makes sense, right? That said, there may be circumstances where still wanting to go through and talking about those main effects might be important, okay? Let's say, and so this is just wanting to sort of drive home, if anybody says this is the way you always have to do things, that's probably not technically correct, okay? Let's say that I go through and I run a study and I'm interested in, I mean, are you interested in older people or people with serious mental illness? Let's say, I was trying to think of some years, there's like health psych types of stuff, right? But let's say what I'm interested in is the relation of smoking on heart disease or something like that, right? And so what I also want to do is sort of take a look developmentally and see kind of what's going on, right? So I run an analysis where I look at smoking, yes, no, on heart disease levels, but I'm looking at different age groups, young adults, middle age, older adults, and so looking at them, right? What I might find in that situation is an interaction of age group and smoking status, right? Where I see that the relation of smoking status on my health outcomes is dependent on age group, right? It's suggesting or assuming that maybe for younger people, it's not great, but it's not as bad as it will be as you start to become older or something like that, right? So here we have an interaction of smoking on age for heart disease, right? And so technically what that interaction would say is the impact of smoking on health is dependent on age, right? And so what we would expect to see is like as people get older and older, so that age exacerbates the impact of smoking, right? And that would be probably what I would spend most of my time talking about. But what I might want to do is if I have main effect of smoking, which I very likely would, I might want to say like, yeah, there's sure age impacts, but also I've got a very clear impact, main effect of smoking here. It's a conditional effect. It depends on age. But smoking is bad for you. Doesn't matter how old you are. In general, we're seeing that people who are smokers have worse cardiovascular health than people who do not smoke. So now, sure, it's moderated by age, but just want to be clear. Regardless, we got this main effect of, or this conditional effect of smoking status. So we'll get into this, but just want to say, make it very clear that we are seeing differences in smoking collapsing across age. Ignoring age, people who smoke are still doing worse than people who don't smoke. Just want to get that out of the way. Here we've got some conditions going on with that. Okay. And so Danielle, it starts to become conceptually, right? Now, I can't just say for always and forever, this is the difference in smokers and non-smokers, because that difference depends on how old they are, right? But in general, maybe it's important, or maybe I want to, in terms of interpretation, to say smoking's bad no matter how you cut it. Just want to make that clear. Even for young people, smoking is no good, right? So that would be a situation maybe, or there are countless other situations where I might still want to make that determination, right? So yeah, Olivia, maybe you're saying, hey, so just so you know, there's juror bias irrespective. Like it's just there. Now it gets worse if we do these things, but it's always there, right? We've got this main effect. This thing seems to exacerbate it, but want to go through and note that there is sort of this effect, and that's often going to be something that's already been demonstrated in the literature and things along those lines. Okay, so for your sets, generally what we're going to do is focus on your interaction, but know for your own research that so long as you qualify that and acknowledge that main effect is not a main effect, it's a conditional effect now, right? In the presence of an interaction. In the presence of an interaction, we don't have main effects. We only have conditional effects. But that conditional effect may still be something worth talking about, even though you may have an interaction effect there. Does that help kind of conceptually think about things? Generally not. Generally, you're going to focus on the interaction, but there are sort of practical reasons why we might still want to go through and talk about that.
So you said for the sake of like, when we do our problems, so you just want, if there is an interaction, to focus on that interaction.
Yeah, maybe unless there's a reason not to.
Well, it's
Just want you to think very carefully about this situation, right? I don't want you to be like, oh, for this class, I don't have, so just think about this, right? So I want you to be thinking about how this stuff goes together.
So if it seems more or less like obvious that there's a main or conditional effect-ish. We can
Yeah.
discuss it.
It just kind of, what I want you to
But
do is.
not in this class.
Yeah, and so what I want you to, and what you should be doing is thinking about, like, every time you go through, anytime you look at your output, you should always be thinking about the question you should be asking yourself, what does this mean? What does this literally mean? So I found a main effect of factor A, okay, but I do have an interaction. So I'm saying, okay, well, what does that effect literally mean? Well, it literally means that collapsing across my other factor, I'm seeing differences across levels of this, right? So ignoring factor B, I'm still seeing differences here, right? Now, this interaction tells me that that difference changes depending on the level of factor B. But now I need to think about, like, is this important to think about? Should I talk about it a little more? Something along those lines, okay? And this comes with knowing your area, knowing what's important, thinking about communications and things like that. All right. Other thing we want to think about, this is where sometimes people will get wrong information. Sometimes thinking about independence of your main and your effects and your interactions. Okay. In this situation, right? We got a 2x2 design. We've got a main effect of factor A right here. Okay. No effect of factor B, main effect of factor A. Okay. Here we got a main effect of factor A and B, right? This is different, nothing going on here. Okay. Here we've got an interaction of A and B, we've got no min effects. No effect here, no effect here, but very different cross pattern going on within your interaction terms, okay? The presence of your interactions or your presence of your main effects and your interactions are by definition mathematically independent of one another. What you will find sometimes is people will say, oh, you can't interpret, if you don't have main effects, there's no interaction for you to interpret, or you can't interpret an interaction in the absence of main effects. That's categorically false. Anytime you get a cross effect, right? And this is the thing, if I were to just look at my main effects, nothing to see, nothing to see. But it actually, in fact, at those different levels, you've got an X going on right here, right? So just be aware that your main effects and your interactions are by definition statistically independent of one another. It does not matter. You can have any combination of these. You can have a main effect of factor A, no effect of factor B, and an interaction, or one of B and not of A and an interaction, or no interaction and one of A and none of B. Any combination, it all works together and puts together with this, okay? So if you've heard, and sometimes like I've had reviews like, oh, you can't interpret this interaction because you don't have any main effects. That's not true, right? So, all right, so for our two-factor ANOVA, okay, we've got three separate omnibus effects, each one with its own hypothesis and set of tests. We've got a main effect of factor A, right? And this is looking at the independent effect of A on my outcome. Got a main effect of B, independent effect of factor B on my outcome, and then I've got my interaction. This is the combined effect of A and B on my outcome. And what we're saying here is that the influence of factor A on my outcome is dependent on the level of factor B. Or I can switch it around and talk about the impact of factor B on my outcome is dependent on factor A. They're interchangeable. They'll often be conceptually a better way to think about it. But again, that comes more with some background and some understanding of your area of things. Questions conceptually about our factorial ANOVA and how we're teasing out these effects. Who's excited about factorial ANOVA? I am. Yeah, Jalen.
I'm excited.
Oh, okay.
My first year project is-
What's that?
My first year project is using.
Awesome, right? So this is good, right? And so as you're thinking about, and this is what I would encourage everybody to do. This is how I learned a lot of this stuff. And I'm trying to pick up a new analysis or something like that. Like in my mind, I'm like, all right, what are variables or what are things in my area that would make, how would I apply this, or what would be a question for variables that might kind of fit into this, try and help try to kind of bring it home, get kind of that conceptual understanding. And then if you've actually got those data, maybe kind of look around, if you find something, now all of a sudden you got a paper on your hands, like half the papers I got is just like screwing around with new analyses, and I go, we can see if we can publish that, right? Yeah, it's a good way to go through it. So yeah, Jalen, as you're thinking about sort of this, like plugging things in, ignore whatever variables I'm getting you, unless your first year project involves trauma, then don't ignore it, then pay close attention. Okay. All right. So what we're going to do in terms of calculating our factorial ANOVA, our two-factor ANOVA, thinking about just like we did with our regular ANOVA, how do we go through in proportion variability, and what do these components mean? How do we piece things apart? Okay. Again, we're going to start with our total variability. This is all the variability in the set. If I look at my outcome and just run the variance of that, that's my total variability. But what I'm going to do is I'm going to go through and I'm going to separate that into between treatment variability and within treatment variability. Olivia, what do we call what's my within treatment variability? What do we call that? Going to be my variability within each individual cell.
Yeah.
What is it? Error. That's the error, right? Because if that grouping thing was the only thing that determined my outcome, everybody should have the same score. They clearly don't. So that there's something going on. There's something causing creating variability in scores that we haven't accounted for. So this is still going to be my error. But what I'm going to do is I'm going to separate over in my between group variability. This is the differences that we're having across our groups. What I'm going to do is I'm going to section this off into a couple different portions. I'm going to have a variability that's due to the main effect of factor A. I'm going to have variability that's due to the main effect of factor B. and then interaction. Okay, so we're gonna separate this out. Everything's still gonna sum to 0. I'm just proportioning this a little bit differently to account for additional factors that I have in my model. Okay, so here, when we set up our ANOVA table, we're gonna have factor A, factor B, interaction, error, and total. We're still gonna have our sums and squares, our degrees of freedom, our means, and our mean squared. Okay, Kate, tell me, my understanding, what is my sum of squares? What do sum of squares represent?
Back at my notes from last class.
Think about like, it's not even last class. If I say, hey, here's some sum of squares, what do sum of squares represent? What kind of statistic is a sum of squares?
Variance of.
Yeah, it's a measure of variability. It's just a raw measure of variability, right? It's literally the sum of the squared deviations from the mean, right? And so my sum of squares is just a raw metric of variability, right? What is my mean squared in ANOVA speak? What does that represent? Variance, not necessarily between groups, it's just a variance estimate, right? Now, depending on where that variance estimate is falling in, but mean squared is just sort of ANOVA code for variance. So this is very literally a variance estimate, right? How do we get variance? How do we calculate variance? Mathematically. How do we get from sum? Can we get from sum of squares a variance? Yeah, what do? Take our sum of squares divided by our degrees of freedom gives me a variance estimate. Okay, so really important and want for this and for always and so for everything we're going to do, wanting people to recognize sometimes like sum of squares, it's like this weird thing. I'm like, I know it's a thing, but I don't understand what it is. It's just sum of square deviations from a mean, right? That's all it is. It's just a raw metric of variability. It's directly related to variance, which is directly related to standard deviation. Standard deviation is just the average difference or randomly selected score from the mean. Like if you sort of think about and sort of understand conceptually what's going on, it takes some of the confusion and mystery out of this stuff, so we can start playing around with this, some of these values a little bit. Okay, so as we're going through, and you've got this handout that is your data for your two-factor this one. I don't know if that's temperature condition, that's the other one. You got a handout that's data for your factorial. ANOVA. Yeah, right here. With this situation here, okay. So this is what we're gonna be sort of building things off of here. In terms of looking at stuff, so if you want to follow along. So our sum of squares total in our factorial design, this is going to be just our total variability in our entire set of scores. Okay, same thing as it was before. Here, sum of squares total is just going to be literally the score for person I in group J of factor A and group K of factor B minus the grand mean squared. Okay. So we've got, in terms of this notation, I just means the individual. J is going to be level of your first factor. K is your level of your second factor. So this is going to be literally, if we're looking at so this group or this table here, I've got people in group. I've got easy and difficult tasks, right? So let's say here again, we're asking people to complete tasks, and we've got two different factors. We've got task difficulty, easy versus hard tasks, and then we've got level of arousal, like activation, like how worked up or how many Red Bulls have we given these people, right? So we've got low levels of activation, medium levels of activation, and high levels of activation, looking at how this impacts performance. Okay, so here for my total variability, if I'm looking at this, I would just take person from easy difficulty, low arousal. So that's 3 minus the grand mean squared plus 1 minus the grand mean squared, 1 minus the grand mean squared, 6 minus grand mean squared, 4 minus grand mean squared. And now we're over to easy medium. So 2 minus grand mean. each individual person in the whole set, the sum of their squared deviations from the grand mean. This is gonna give us our sum of squares total. Okay, this is all the variability in the sample. Okay, this is what we're gonna split into between versus within group differences. And the sum of squares for my total is just gonna be the total number of people in my design minus 1. So here, if we look at your handout here, sum of squares total is, we can calculate this computationally as the sum of my squared x's minus the grand total squared over n, right? So we're just pulling this these values off of your sheet here so you can see where those are from. And then your degrees of freedom total. Drop those into your output. Okay. Questions on sum of squares total? So thinking about sum of squares error, this is the same thing as it was in your one-way ANOVA. It's just the variability, the combined variability within each condition or group here. Okay. Thinking about this conceptually, what this is it's the sum of the square deviations of individual people in level 1 or level J of group of factor A and level K of factor B minus the mean of that group. Okay. So what we're saying is we're just taking, for each individual, taking the square deviation of their group mean and squaring that up and summing these all up together. Okay. Some of the square deviations of person K at level I of factor A, J at level factor B, right, from their respective cell means. Okay. So if I'm looking at here, again, if I'm looking at my low easy group, it's 3 minus 3, 1 minus 3, or 3 minus 3 squared, plus 1 minus 3 squared, plus 1 minus 3 squared, plus 6 minus 3 squared, plus 4 minus 3 squared. Add those up and then do the same thing for the next cell and the next cell and the next cell. Add these up. This is just the sum of the square deviations within each one of these cells. Okay. Again, variability within cells due to individual differences, experimental error, systematic things that we may not have accounted for. All of that stuff is going into my error term. Now, my degrees of freedom for this is going to be now the product of the level of factor A, the levels of factor B, and the number of participants minus per cell minus 1. So if I've got the number of levels of factor A, levels of factor B, times the number of people minus 1 per cell. Or I can get degrees of freedom error by subtraction. If I take the total minus degrees of freedom A minus degrees of freedom B minus my interaction degrees of freedom, I'll go through and get my degrees of freedom error that way. So here, the data that you have, what we can do is we can just go through and calculate your sum of squares error as the sum of your sum of squares for each group. If you look at this, you can just add up the sum of squares for all 6 cells, which will give you your answer, your degrees of freedom, A times B times n minus 1, 2 times 3 times minus 1, because we got a balanced design here with 5 people in each group. Go through and calculate this in, and now we've got our sum of squares error within treatments or within subjects group. Got this? Okay. All right. Now I'm going to go through and calculate sum of squares for factor A. Sum of squares for factor A, this is the variability or differences across levels of factor A collapsing across other groups. Okay. What I've got here is my sums of squares for factor A. If n is my cell size and B is my levels of factor B, right? What I've got is the sum of my square deviations of the mean of level I of factor A from the grand mean multiplied by the cell size levels of factor B. Okay. So here we've got number of people per cell, number of levels of factor B times the sum of the mean of level I of factor A minus the grand mean. Okay. So if I'm looking at here, that summation here in the middle, if I take the mean of low minus the grand mean squared plus the mean of medium times the grand mean squared plus the mean of high minus the grand mean squared. Again, it's just those marginal means that we're taking in. What we're doing is that we're looking at variability across those groups. Okay. Computationally, we can go through and calculate it this way. Degrees of freedom for factor A, or for sum of squares A is just degrees levels of factor A minus 1. So again, here, just plugging in information from your sheet, so you can go through and see that. Degrees of freedom is the levels of factor A minus 1. For factor A, we've got, is it 2, 3, 2, yeah, 2 minus 1, and dropping that in there. People see where we got these numbers from conceptually. What we're just doing is, again, looking at here, and we think about what our main effect is. It's those marginal means that we talked about, right? So we're just looking at literally, it's the difference in, I guess for factor A, it's going to be 6 minus the grand mean squared plus 2 minus the grand mean squared. That's given us the variability across those two groups. Collapsing across group factor B. Factor B is the same thing. We're just going to go through and take the marginal means of for factor B. So here we're looking at arousal collapsing across difficulty. So we're going to here, this is where we're going to take 2 minus 4 squared, 5 minus 4 squared, 5 minus 4 squared, take the sum of the squares of that, and then multiply it by the cell size times the levels of factor A to go through and get variability across my marginal means for factor B. Okay. And then calculate my sum of squares the same way. Okay. So again, here, sum of squares by calculation, right? So based on plugging in information from our sheet, and then my degrees of freedom and dropping that in here. All right. Now we get to sum of squares cells, okay? Sum of squares cells is going to be the variability or differences across my cell means, okay? This is a computational figure and not something that's typically included in my classic ANOVA table, okay? In SPSS, what you'll see is your sum of squares cells is listed under corrected model. If you wanted to see this in sort of your SPSS output, this is where it would come from. Essentially what this is, it's computational and factorial ANOVA, but essentially what your sum of squares cells is similar to what your sum of squares between was in your one-way ANOVA, right? You're literally just taking the variability across all of your cells and using that to calculate your sum of squares cells, okay? Your sum of squares cells is going to take systematic differences due to factor A, systematic differences due to factor B, and systematic differences associated with the combination of those two effects, okay? So again, remember when we were doing our one-way design, we had sum of squares, between, which is kind of like just, but we only had one factor, and so it was just the differences across our cell means. Sum of squares cells in factorial ANOVA is just treating all those individual cells as their own groups and looking at the variability across all, in this case, 6 cells, okay? So conceptually, what we're doing is we're taking the sum of the squared deviations of the mean of level I of factor A and J of factor B minus the grand mean and squaring those up, okay? So literally here we're taking 3 minus 4 squared plus 6 minus 4 squared plus 9 minus 4 squared plus 1 minus 4 squared plus 4 minus 4 squared plus 1 minus 4 squared to go through and square those deviation scores to get the variability across all my individual cells. Okay. And that's kind of getting all the between group differences here. My sum of squares cells is going to be equal to my sum of squares total minus my sum of squares error, right? And so this starts to make sense because if we think about my sum of squares total is the total piece of the pie. Totals is all the variability that I have. And if I go through and I take all the variability I have and I pull out what's due to error, what's left over is just due to systematic differences due to the stuff that I've accounted for. We'll kind of see where this is coming from. So sum of squares cells in this case, we're gonna take sum of squares total minus sum of squares error. It's gonna give me my sum of squares cells. This isn't located in the table typically, it's just something that we're gonna use for calculation. All right. So sum of squares for my interaction, right? This is the variability mean the combined effects of factor A and factor B. What I'm gonna do is I'm always gonna get sum of squares for my interaction. I'm gonna get this through subtraction, okay? So sum of squares AB is gonna be my sum of squares cells minus sum of squares A minus sum of squares B. This is gonna give me my interaction stuff, okay? So here, again, looking at our kind of figure, this is the whole pie. This is all the variability that we have to work with. We've sucked out the stuff that's all due to within group differences, right? Because we don't know why those are different. It's for some reason it's not accounted for by our model. We're gonna pull that out, right? And then we calculate variability to factor A, variability to factor B, and then the between treatments variability, we calculate that as our sum of squares of cells, right? So if this is cells and I remove factor A, remove factor B, what I've got left over, that's my interaction. So we go through sum of squares for my interaction is going to be the degrees of freedom A times the degrees of freedom B, multiply a product term there. So here, what I would do is I take my sum of squares cells minus sum of squares A, sum of squares B, get my sum of squares interaction, and then take my, oops, there we go, and then we'll take my just taking this from the total and sort of moving from there. So just showing you just different ways to go through and do that. And then take the product of my two degrees of freedom there for A and B, and it gets me my sum of squares for my interaction piece. All right. So once I've got that all figured out, then everything's easy peasy from that point on, right? And now, again, what I'm going to do is I'm going to calculate my mean squared error and my F's. The mean squared error is just my sum of squares error divided by my degrees of freedom, right? So this is easy. Let's jump ahead. So within mean squared within, which is my mean squared error, 120 minus 24 gives me my mean squared error. Once I've got my mean squared error, I'm going to go through, calculate my mean squared for factor A, then take my mean squared for factor A divided by my degrees of freedom error, or divided by my mean squared error is going to give me my F statistic. Same thing. Sum of squares divided by degrees of freedom gives me mean squared for factor B. Mean squared for factor B divided by mean squared error gives me my F for factor B. And then mean squared divided by degrees of freedom, mean squared for my interaction. Take that divided by my error term gives me my F test for that interaction term there. Okay. And now what I've done is I've gone through and completed and filled out my full ANOVA table here. Okay. We'll see how I sort of, again, it's just the same thing. It's just all kind of summing at zero with this, which makes this a nice way to go through and check stuff. Sound good? Okay. So thinking about our ANOVA test here, I've got 3 statistically reliable effects, as these are all massive F values here, right? I've got a significant effect of A, which is my task difficulty. I got evidence for an effect of B, which is arousal, and then I have an interaction of A times B, okay? And because in this situation, we have interdependence, this is a situation where I would probably just go through and focus on the interaction here, as opposed to sort of worrying about the main. I really don't have a strong rationale for like saying like, no, we really need to sort of communicate what's going on with these effects, because these are no longer main effects. With this coming up as positive, these are now conditional effects. So I can't even really talk about main effects, right? I mean, I could, so long as I know what I'm talking about, but going to focus on this interaction term. Okay. And so again, evidence of an effect of an interaction effect here suggests that my effect of arousal on performance is conditioned on task difficulty, right? If you ask me, hey, how does physiological emotional arousal impact performance on this? I'll say, I don't know, are we talking about difficult or hard tasks, right? So we have a conditional effect. If I go through and plot this out, here's what I've got going on. Allison, what's going on in this graph? What, just looking at it, what seems to be the nature of the interaction of arousal and task difficulty on performance?
The easier tasks, better performance. Like the easier the task, the better performance.
Yeah, so if I've got, so I could look at this and say, just looking, and this is, we'll start to get into like looking at this, the easier the task, the better performance I have, right? But I could also look at what's the relation of arousal with performance at easy level for easy tasks.
Wait, say that again.
Yeah, what's the association of arousal on performance for easy tasks?
Higher arousal on easier tasks is associated with better performance.
Yeah. For easy tasks, as arousal increases, performance increases. Okay. What about though for difficult tasks? What happens here?
Like we got like the two extremes, so like lower and higher arousal. Performance decreases.
And so we got kind of a Goldilocks effect going on here, kind of that inverted U, right? Like for difficult tasks, if I'm not agile, if I just woke up or so I'm like tired, performance isn't going to be great. If I'm too much, if I'm too anxious, if I'm too worked up, things aren't going to be great. But if I got just the right amount, that's where my performance is going to be best for this difficult task, right? And so what we can see is very clearly, if I go through and draw my line, right, I've got very different patterns going on. It's very clear to see this interaction. So if you ask me, what's the impact of arousal on performance? I don't know. Are we talking about easy task or hard task? It makes a big difference. If we're talking about easy stuff, when I get work there, so the more active I get, sort of the better performance gets. But if I'm talking about more difficult things, now all of a sudden I've got kind of a sweet spot, right? We got an optimal level of arousal. If I get too much, performance goes down. If I get too little, performance is going to go down. And so what I would say is the effects on arousal, effective arousal on performance is conditioned on task difficulty. Or I could switch it around and I could say the impact of performance on task difficulty is conditioned on arousal. Either way, we want to go through and talk about it, whatever makes the most sense. People kind of see what's going on with this interaction and how we would go through and interpret that. Let's not waste time on this. Okay. I want to finish up talking about power of our factorial designs. Okay. What we find is our factorial designs are often going to be more powerful than the one-way ANOVAs that we were using before. Okay. And what happens is as we go through and we start to, within reason, start to account for some additional sort of variables or potentially different additional influences on sort of whatever my target outcome is. What happens is these additional factors are kind of act as covariates. They start to account for variability in my outcome, right? So again, human behavior is really, really complicated. There's never like one thing that determines an outcome. As I start to account for more factors, I start to account for more systematic variability. So what happens, Jalen, to my to that variability in my one-way ANOVA, all those differences within groups that I didn't know what was going on with, as I start to add in and layer in other factors that might account for that, what happens to the variability within my groups? It's going to go down, right? And so if my variability within groups goes down, what does my error do?
Goes down.
It goes down because I've gone through and I've accounted for stuff. And if my error term, if my mean squared error in my ANOVA table is smaller, what happens to my F tests?
Bigger.
They get bigger, right? Basically, you can think about this from a regression standpoint, and this holds in regression. The bigger my R squared is, the more variability my outcome I've accounted for, the more powerful my test is. because I've got less air, I've got less static, I've accounted for more things. Now, we can go nuts and put too much stuff in there and then things kind of fall apart, particularly if we get redundant variables. But what we see is because with our factorial ANOVA, because we've added in additional things to account for whatever it is we're trying to account for, what we tend to see is our factorial designs tend to be more powerful than our one-way design. So again, for example, here I'm looking at the impact of arousal in response to amusement and anger, elicit fear, anger, and amusement stimuli, right? So something that I would look at in a one-way ANOVA, right? So I've got looking at emotional arousal. Some people watch fear-related stuff, some people watch amusement-related stuff, some people watch anger eliciting stuff, right? So here's all the variability in my outcome, here's the variability due to my film, and here's just my big old error term, right? And so maybe I do find differences across these groups, right? But maybe now in study 2, I've got the same thing, but this time I go through and maybe I have film condition, but I take participant sex into account, right? And say, I don't know, do people who identify as men and women, are we seeing sex differences in how people respond to these films, which seems like a reasonable thing to expect, maybe, right? Now, all of this variability within each one of these groups that may have been done attributable to whether or not my participant was a man or a woman. Now all of a sudden I've accounted for that, I've modeled that. And now what we've done is we've taken that out of the error term and now we've captured that as a sex effect within my design, right? So now that variability that used to camp out here, we've accounted for it. This is smaller, and as Jalen said, now our error term is smaller. That's what's in the denominator of all my F tests. If that's smaller, my F test goes up. I've got a more powerful test. Okay. Kind of see how sort of just the nature of the design and accounting for more things starts to impact and sort of increase my power. All right. Effect sizes here, we've got a number of different effect sizes for our factorial ANOVA. Again, we've got our eta squared. This is just going to be my sum of squares effect over my sum of squares total. This is the proportion of total variance attributable in the sample. So interpretation is just the exact same as it was for our one-way design. Okay. Again, we see that this is positively biased. Now my other thing too that will happen with my eta squared is my eta squared will start to systematically get smaller with the number of effects that I have in my design as compared to my one-way ANOVA. Okay, so for my one-way ANOVA, I just have a sum of squares effect for factor A. For a 2x3 ANOVA, now I have a sum of squares effect for A, for B, and for the interaction. Okay. What starts to happen is if there's any shared variability, now this happens less if I've got an experimental design where everybody's randomized to different conditions, but if I'm looking at pre-existing groups, right, now all of a sudden the things that sort of factor A might be related to factor B in a way, right? And so what we're only getting with this is the stuff that's unique to factor A. And so what happens is then relative to factor A, where I get sort of everything that's due to sort of this factor, as I start to layer in other things, that starts to kind of chip away at the variability that's unique to that factor. And so what ends up happening is my eta squared, as measured in a one-way ANOVA, will become systematically smaller, or tend to become systematically smaller if I'm looking at that same effect, but within a factorial design that's accounted for other things in the model. Okay. And so what happens then, need to be aware, if I'm looking at one study that's reported an eta squared based on a one-way design and an eta squared that's based on a factorial design, recognizing that there could be systematic differences, shrinkage in that eta squared from the factor, from the design that's accounting for more things. Other thing that we have that's unique in terms of our factorial designs, what we get now is a partial effect. Okay, partial effect, partial eta squared is going to be indicated. So if my eta squared is the sum of squares over my total, right? This is kind of like a mini R squared, right? Of the total piece of the pie, how much is attributable to my observed factor here, okay? Partial eta squared, you can see a little bit of a difference here. What I've got is the sum of squared of effect or variability of my effect over my variability of my effect plus my sum of squares error, okay? What I've got here is, this is the total piece of the pie, right? And so here's my sum of squares effect due to factor A, right? Eta squared takes this relative to the whole thing, right? Okay, let's have a two factor. Eta squared, sum of squares of effect relative to all the variability in the model, right? So it gives me something that's pretty easy to go through and interpret. Partial eta squared, this is going to be the sum of squares effect over the sum of squares effect plus the sum of squares of error. So now let's say I've got, this is going to be equal to A over A plus C, okay? Relative to eta squared, what's going to be, which is going to have the smaller denominator, partial eta squared or eta squared?
The eight square.
Which one's going to have the smaller denominator? Partial eta squared, right? Well, partial eta squared is saying, okay, if we take out variability that we know that's attributable to other factors, if we pull that out, right, what's left over? If we ask of what's left over after we control for this other stuff, partial eta squared is telling me of what's left over, how much is attributable to factor A. Okay. So what ends up happening is we're saying partial eta squared is the proportion of residual variance unaccounted for that's attributable to a factor that's unaccounted for by other stuff. Okay. So in a nice experimental design where everything should be orthogonal, or factors should not be related to one another, if I take out everything that's due to factor B, of what's left over, how much of that is, how much of whatever's left over is attributable to factor A, okay? So we would call this a partial effect. It's controlling for other things. If we take that out of the piece, we've already accounted for it, so we don't care about that. Of what's left over, of what we would call error, how much of this, what proportion of what's left over is attributable to factor A. And what this ends up doing is it's being useful for comparing effects across different studies with different numbers of factors. Problem with our eta squared is as the number of factors increase, that's going to start to shrink it up a little bit. So it's kind of an apples and oranges comparison. Partial eta squared, because it's a partial effect, it's counting for what proportion of variability is left over after I account for this other stuff. It starts to be more useful in comparing effect sizes across different types of designs. Again, less meaning, it has a more difficult meaning conceptually, right? Because I'm saying of what's left over, how much is this accounting for, right? But still tends to be biased in terms of upward bias, but a nice way to go through and compare across different designs. Okay. And partial eta squared is important for the calculation of power. We can take partial eta squared and turn that into an F. F is the formal effect size for calculating power. F doesn't have a real good interpretation, but we can go through and do that, and we can report effect sizes as F there as well. All right, we'll revisit this because now we need to go through and talk about omega stuff too, which is just sort of population estimates of the other thing. So we'll revisit this when we come back after Thanksgiving, but that'll do it for today. Any questions about this stuff? At least immediately right now. All right. Kind of a lot to wrap your head around. It's a lot of things to start kind of thinking about how things fit together, but are people feeling at least sort of okay-ish about this? Okay, awesome. Thank you so much. You all are champions. Go through, make sure to be picking away at this next set. I'll be around if you're running into questions, things along those lines. Just reach out. I'll help you out, get you squared away. Okay. Awesome. Thanks, everyone.
Yeah.